Okay, we are going to do this board work style problem the way that you're familiar with doing them. But first, I'd like to just say that, with the last one, it did undetermined coefficients for us. And what I want you to see about the Laplace transform is it does everything for us. I would hope that you can look at this and see the issue that comes up that makes it not quite as straightforward as um, as these problems would be, like finding the XC, for example, with this one is super straightforward. With this one, there's a little bit of a bump in the road. You guys should know how to deal with it, but I just want you to see how the Laplace transform recognizes that itself and takes care of all our decision making for us. So what I'm going to do in a moment is I'm going to tell you in a moment to hit pause and do the problem yourself. And I'll just have the whole problem all the way done out after, like 5 seconds or so, and I'll walk through that problem. I'm going to talk about what it does at the end. So I'll give you a timestamp for where to go. So hit pause, see if you can do this one. Here comes your solution. Here's our solution. It is e to the t minus t e to the 3t. I want to point out that, if you got that, awesome. Go forward to the timestamp that I list out for you, whether it's in the like description or the description below, or whether it's on a Google Doc. But I'll go through the whole process. So I Laplace this thing. It was really nice that I had ones and ones here. Oh, by the way, I'll say I just like sort of made this one up out of nowhere, and I was totally shocked about how nicely things worked out. I don't know if I've ever had something like this equal to zero, and I've been doing these problems for 14 years. But anyway, Laplace this thing. It was really nice that I had ones because I didn't have to really think about it much. It was just minus 1 times s, minus 1, minus 6 times sx minus 1. And then the 9, and then this was the Laplace of that. I just distributed everything, and then I grouped these guys. S squared minus 6s minus 9 is the x pieces. The 1 over s minus 2 was here. When I combined my like terms here and moved them over to the right-hand side, I got s minus 5. This work right here is putting it over an s minus 2, so creating that common denominator. This foils out to s squared minus 7s plus 10. Add the 1 to it, I get s squared minus 7s plus 11. I divided by this and factored, so I got the s minus 2 times an s minus 3 squared. The s minus 3 is the piece that's repeated. So I got 1 over s minus 2, I got something over s minus 2 plus something over s minus 3 plus another thing over s minus 3 squared. From there, here's my cover-up work right here. S equals 2. I did that math and got 1. S equals 3. I did this math and got negative 1. And then S equals 0. This is the one that I was like, what? Because I really just made it up, S equals 0. I got, what I did was I plugged in 0 for all these. Remember, it's really nice to plug in 0 because all the S terms just go away. So it was 11, the top, times negative 2 times 9. That's this. And then the 1/2 comes from 1 over the 2, negative. Minus, should that be a plus? Oh no, sorry, that is a minus. The minus comes from this negative 3 here, on this a over 3, and then minus 1 over 9. So from there, I wrote out what I would type into my calculator. This would be just 1 over 2. Negative 11 over 18, because I'll do that multiplication. Times negative 3. I didn't show that in the last video, but you can do that. You can do this, all this stuff, hit enter, and then multiply by whatever is underneath the A. And I was like, whoa, I got 0. So anyway, you get 0 here. And then we inverse Laplace that thing. And this goes to e to the 2t. And this guy goes to negative t e to the 3t. Now, here's a spot where I hope that if you got it right, you're coming back into the video and listening to what I say here. In the beginning of this video, I kind of talked about this one. And I talked about, it does undetermined coefficients for us. What I mean by it is I mean the Laplace transform. it just takes care of that, right? I don't have to do any work for it. Well, I do. It's all this work, but I don't have to make a decision about what to do. I just apply the math we know, right? It's not like, well, if we do this thing, then that happens. If this thing, then that happens, right? I just do the math. So here, I've got a repeated root, right? I got this x double prime minus 6x plus 9x. If I were to do the characteristic equation, it would give me r equals 3, comma 3. And what we learned in the last unit was that you tack a t on to that extra piece to create that linear independence. Well, look, we don't have to memorize that. We don't have to think about that. The Laplace transform, by getting this squared term, gives me that t e to the 3t. Same thing would work if I had a resonance problem, or if I had a problem like this is called a repeated root, that 3. A duplicated root is when I have a root from this left side match a root on the right side. And I've got rules for that too. And that's what we called resonance in like an applied setting. So what is magical about the Laplace transform is that, one, it gets rid of derivatives. And it's not really magical. I could go into like more of a this is why it happens, right? But just like big picture, what is magical about the Laplace transform is that it gets rid of derivatives. I apply it, boom, first line, no more derivatives. And then it just turns this like pretty complicated problem, and I agree, this math here is complicated, but it's just algebra. It turns this pretty complicated problem into just algebraic manipulation. Factoring, moving things over, multiplying, splitting some fractions up. It's all algebra. And then I get it into a nice form, and it gives me my answer. And I hope you're starting to see that about the Laplace transform. And then there are other things that are extra special about it that we will do later. So, sweet. Thank you, and I will see you soon.